All right. So I need to add up all of those values. So you're going to have to go back and show me. I think I had 2,400 joules, right? So 2,400 joules plus a negative 259 point something, is that right? 0.8? Plus a negative 600 joules, is that right? So when I add those two up, what am I going to get? Around 1,600 and something? 1540.2? And it's positive. So that's the work, the net work done. So I'm going to take the net force and multiply it by cosine of theta times d and see if I can get the same thing as the net work done, and I know I will. So the net force, well, I had 200 newtons up the ramp. And what was friction? 21.6. Okay. And then my other work was, my other force was 50 newtons, is that right? And then my cosine is going to be cosine of 0 because I'm going to be shoving it up the ramp. So the force, net force will be up and the distance is up 12 meters. So that should be the net work done. And I'm hoping you're going to get 1,540.2, but somebody better check me. Yes? Okay, so they matched. And that's exactly what it said they should do. So I'm all good. Okay, let me point something out. I did not do the work done by the force normal. Let's talk about why. The force normal is up that way. The motion is that way. What's the angle between those two? 90 degrees. What's the cosine of 90? 0. Check it on the calculator. So that's why there's no work done by the force normal. On your test that some of you struggled with. There was a question about, on one of the tests, about F and V. And that's what goes on with centripetal motion. So if you look at that angle, what's that angle between those two? 90 again. Is there any work done by F when V is pulling inward? Or any work done on the object when the motion is toward the center of the circle? No. If F and V are at right angles, no work is done. So there's no change in the kinetic energy. From here, the only thing I would take from here is the fact that energy is the ability to do work. So that's really the only thing you need right there. The ability to do work. We need to concern ourselves with the fact that we have two forms of energy. If this thing will let me write. There's your first form. And I don't use K, I use KE. It's equal to 1/2 mv squared, where m is the mass in kilograms. And b is the speed in meters per second. Our PE is energy because of position, and it's going to be mass in kilograms. G is our 9.8, and H is our height in meters. Now, if you do those, okay, this is often called the work energy theorem. And basically what it says is that if you do any work on an object, you have the potential to change its energy, kinetic energy. So if you think about it, it makes a lot of sense. If you have a block that's moving at a certain rate and you continue to apply a force, it's going to get faster and faster, so the kinetic energy is going to change. Work done is going to be equal to KE final minus KE initial, which is just the change in KE. We always do final minus initial. This one. Okay, it says find the kinetic energy of a 3,200 Newton automobile traveling at 75 kilometers an hour. Well, we know that KE is 1/2 mv squared. However, we don't have the mass of the automobile, we have the weight, so we're going to take that 3,200 newtons and we're going to divide it by 9.8 to give us the mass. So the mass is going to be 300 and, I don't know, 19 or something like that. Somebody can do that for us. 300 what? 326 kilograms. That works. We definitely can't leave the speed like it is because it's in kilometers per hour, so that's 75,000 meters every 3,600 seconds. So we're going to get 20 point what? 20 point what? Beautiful. 20.83 meters per second. That's our speed. Now we can get our kinetic energy. All right, so there I have plugged in 1/2 mv squared. Would someone do the math and tell us what they get? It's around 6,000 and something, I think. Ashley, did you get it? Nope. Force of gravity. What'd you get? 70,000? 71,000? 70,724? There's any decimals? Eight, 9? Good enough. And that'll be in joules. Okay, so we need to fix that right there. Thank you. 70,723.89 joules. All right. Do you have that one in your notes? Yes? Okay. So we're looking for the force. Now, we know the mass is 16 grams, 0.016 kilograms. We know the initial speed is 260 meters per second. And we're going to stop it, so the final is going to be 0. Garrett Gray, are you paying attention to me or paying attention to him? D is 0.12 meters. So the change in KE is going to equal the work done on the bullet. So that's what my equation looks like. 1/2 mvf squared minus 1/2 mvi squared equals FD cosine theta. All right. This will be 0 because we're bringing it to a stop. So I have a negative 1/2, bless you, 0.016 kilograms. DI was 260. Don't forget to square it. Is equal to F. Well, the force is going to be acting in a direction. Okay, if the bullet's going in and the tree is stopping it, the force is going to be acting in an opposite direction. So that's going to be cosine of 180. It's a retarding force, so it's going to stop the motion. And it's going to stop it in 12 centimeters or 0.12 meters. So we should be able to solve for our force. Okay, so the retarding force, right there. Now, would you agree we could have done it F equals ma? Because we could have found the acceleration. But this is a lot simpler. I think you'll find that this works a lot easier for you. Look at this one. This is a potential energy one. So we know that PE is equal to mgh. Oh yeah, right here? Or right here? Okay, we're going to talk about why that is. All right. Now, we want to find it relative to the bench top. So here is our top of our bench, and I'm 200 millimeters above that, or 0.2 meters. My bench itself is 1 meter off the ground. So right now, if they want it relative to the bench top, I'm only going to use the 0.2. So I have 250 grams, which cannot stay in grams. So that's 0.250 kilograms. Gravity is 9.8. And my height is 0.2 meters. I have to have it meters. So I think I'm going to get 4.9 joules, but I would appreciate it if somebody would check me and make sure that that's good. All right, so I should have gotten 0.49 joules. Okay, because 2/10 of that is 1.96, a fourth of that is 0.49. All right, everybody okay on that one? Can we move forward? All right. Part B says we want it relative to the floor, so the PE is equal to mgh is still my equation. The only difference is I've changed the point that I'm interested in, so 0.25 kilograms. Gravity is 9.8. And now this is going to be 1.2 meters because I want to go from, nope, that's a lie. No, it is right, yeah, because I'm 200 millimeters above, so I want to go from where I am above all the way to the floor, so that's 1.2 meters. All right, so now I'm going to do mass times gravity times height and solve for my PE. Okay, so there's my potential energy relative to the floor. And notice the potential energy is always relative to some point. You have to know where they're talking about. Work done is equal to the change in potential energy. Remember a while ago I had work done, if it'll let me do this, was change equal to change in KE. Well, I can also say that work done is equal to change in PE. All right, so let's move on. Because if I lift something, I'm changing its potential energy, and I have to do work to do that. Now, there are two kinds of forces, conservative and non-conservative. All you have to really concern yourself with here is that friction is going to be our non-conservative force. I can do 15 minutes and put it on my YouTube account. Okay, so friction is a non-conservative force. It's going to, that'll be negative work. Because friction is going to take energy away. And that's the only real difference. Now, you have seen this before hundreds of times, law of conservation of energy. The way it's going to look in physics is you're going to say KEI plus PEI will equal KEF plus PEF. Because this is the initial amount of energy, this is the final amount of energy, and they've got to be equal to each other. As he holds that stone, all he has is potential energy. As he releases it, halfway down, it's half KE and half PE. When it gets all the way to the ground, it's all KE. This relationship is going to make one of those problems that we're going to work, several of them actually, so much easier because you don't have to do all the crazy VF squared equals BI squared plus 2AD and all of that kind of stuff. It's not necessary if you understand what's going on with conservation of energy. And these three bars right here are helping me to figure out what's going on with the energy. So if I look at it, my cart should, if it'll come back, and I'm not sure if it'll be animated since I'm trying to record it. Let's see what happens. If you look at this one right here, you have potential energy, and you have a cylinder with a piston across the top and motion of gases right here. As you allow that potential energy to convert into kinetic energy, it drops and falls on this piston and drives that piston down and makes it fall more and more. Well, what's happening is these are getting closer and closer, so they're bumping into each other more. And so as they move faster and faster, they generate more kinetic energy, and the temperature will rise in this gas sample. If you shoot off a projectile, and you know we all love to projectiles, okay, what happens is all of this KE here, because of the chemical energy released when it's shot off, all of this KE converts to pretty much all PE here, and then converts back to all KE here. Okay?